So thanks all. This is a big crowd, and I'm quite excited about this. And so just to introduce myself quickly, my name is Pandit Madan. I'm a PhD student at Harvard, and I'm also a research affiliate at the Center for Brains, Mind, and Machine at Harvard and MIT. And today we'll be talking about something that you might have heard about in the news. So just a show of hands, how many of you have heard the term AI recently, somewhere or the other? Great. So a lot of us have, and we'll try to understand a little bit more about how this works, what happens here. So before we talk about AI, let's talk about the real keyword here, right? We are saying something about artificial intelligence. So the natural question, first of all, is what is intelligence? So what comes to mind when I say the word intelligence? To some of us, it may be these amazing new technologies that companies like Facebook, Amazon, Google built. To others, it may be this robot that you see in a sci-fi movie like Ex Machina or Star Wars or a bunch of other sci-fi movies that keep coming out these days, right? To some others, it may be their pet because they seem to be very intelligent. They exhibit a lot of complex behavior. They can do these amazing things that stump us all the time. And to some, it may just be all of us sitting in this room. We're all intelligent. We're able to do complex things. We can solve machines. We can solve tasks. We can build amazing buildings, write beautiful stories. We can do so much in plain sight that we always take for granted. So that begs the question: what is intelligence? Would you say Apple's Face ID is intelligent? Or maybe Google Translate? Or maybe all those advertisements that Instagram shows us, which are always spot on? So I've asked this question as a poll multiple times in previous classes or public lectures. And the short answer is that people are always split. There's no clear consensus on whether people would say these are intelligent systems or not. But one thing everybody seems to agree on is that this robot is intelligent. So this is a clip from a movie called WALL-E, which is one of my favorite movies. And as you can see, the robot here watches the cockroach. It steps on it. Oh, that's unfortunate. Sorry about that. Here we go. Let's give it another shot. So the robot steps on a cockroach and realizes that's something bad. So it steps back, presses fear, and then it communicates. So it says, get out of my way. It walks around, it's able to walk in this complex terrain, and it gets the job that it's been given to do. It starts doing this job of packing garbage together. That's the job of this robot. It finds new objects it hasn't seen before, and some of them it's going to think are useful to keep, so it has a box behind it where it's going to retain objects that are useful. So it keeps toys, like little toy doggies. Some objects are not so nice. Right, so it has a purpose and it's fulfilling that purpose, doing that job, just as all of us do. Sometimes it comes across new objects. So it's never seen a fire extinguisher before, and it sees that, and it tries to understand how to use it. So whenever I show this video, there's almost some sort of consensus. People always think that this robot seems to be intelligent. So we sought out to find what is the definition of intelligence. We had a hard time understanding what it is, but we seem to have found something which we would sort of agree is artificially intelligent. So let us just define intelligence as the complex behavior that this robot is able to do. Whatever this robot is able to do, let's call that intelligence. And let's talk about what are the capabilities that are exhibited by this robot. So it recognized the cockroach. It was communicating with the cockroach. It was walking around in this complex new terrain that was never seen before to it. It was curious, so it found new objects. It was excited by them. It was also learning to operate objects it hadn't seen before. And lastly, it knew how to get back home. It was able to plan its route and get back home. So now that we have some idea of what we mean by intelligence, the next question obviously is, how do we teach all this to a robot? If we today were going to start building WALL-E, how would we teach WALL-E these skills? And this is where another term that you might have heard about comes into play. So a show of hands again, how many of us have heard this term called machine learning in recent days? Right, so a lot of us have heard about it in the news. And for those who haven't, I'll just explain what it is. Essentially, the idea is you take an unprocessed data, you apply a toolkit on it, and that toolkit transforms it into something more basic. So, like you take this block of wood, put it through these tools, and what you get out is a chair which is much more useful. Now, more concrete examples of what might be happening is that you take a picture of chair, you throw it inside a system, in a computer program, in an ML system, and that spits out the useful information saying that this is a chair. Similarly, you may put in information like there's a 21-year-old who speaks English and just got into a new relationship. So Spotify should probably play music like Ed Sheeran for it, because that's something that you know this person might like. So the key takeaway here is that intelligent tasks often involve extracting useful information from raw data. You have something which you don't understand, some complex data set that you collected. You want to extract something useful from it. You use ML to extract that stuff out. We saw this example of this chair picture going into a system, and the system telling you it's a chair. But before we understand about how this ML tool can extract useful information, let's first try to see the raw data itself. Let's see how a computer sees the picture. So on the screen here, what we have is this beautiful image of this complex new world which has 2 moons, a beautiful house, there's green grass and who will not live here, right? And that's how we see this. But let's see how computer sees this picture. So if I pick out a small region from this picture, what you'll see is that a computer actually sees it like this, which is a large grid of numbers, a large table full of numbers. It's not very beautiful, right? So computers see pictures as very large grid of numbers, and the trick to understanding them is to find the right subset of information in this large big table which might be boring to us. That's where neural networks come in. That might be another term that people might have forgotten. So if you heard about neural networks or deep learning in the news, what's happening there is that you take this picture, it passes through something complex, which does a lot of math to it, and then selects a subset of information that might be useful. So scientists spent years, decades, trying to find the right subset of information to pass into a machine learning system. For 50 years, people have worked on finding and telling if this is a chair or not. But then along came neural networks, and neural networks were able to do this thing much faster and much better than humans could. So the whole idea is that deep learning is a tool. If you've heard the trick phrase, next time you see it, all you need to think of it as is a hammer inside a toolbox. You have a toolbox which can take raw data and give you interesting, useful information. And deep learning is one of the tools inside this toolbox. And it has unprecedented success. We're able to do things like Google Translate, which can translate between languages. We're able to do things like automatic cell detection, automatic tumor detection, which is extremely helpful for doctor and healthcare. It can do things like language processing or speech recognition, which is an example of Siri, and even self-driving cars, which are all super cool, and they're great successes we could not have done before, maybe 10 years ago or 15 years ago. But there's a serious problem. One problem is that since these systems are extremely susceptible to small changes. For example, here's a great example of what happens with these systems. You have this picture of a panda, and you pass this to one of these computer vision AI systems, and it tells you this is a picture of a panda. But now we add some kind of weird noise to it, which humans can't even see. And you pass inside these systems, and you see that the system now thinks it's a gibbon, it's not a panda anymore. This is a huge problem because humans are not affected by this thing, but this machine is. So such a system can be attacked in this way, where you may add some little noise, and you don't see the difference, but the computer vision system breaks down, the AI system breaks down. Another example is this picture that I show here. We passed the first picture inside the AI system. It's going to say it's a vulture. Just rotate it a little bit and pass it, and it's going to say it's an orangutan. There may be other problems like biases. So we know that AI models trained to predict who's going to relapse and cause another crime. They're racially biased. There's also systems that try to understand who's a better employee, how to hire a better employee. They're also racially biased. So these are issues that have real ramifications in the real world around us. And the question is, how do you find them and how do you fix them? So first of all, let's try to understand why it's hard to study them. So what I'm going to show here next is a schematic. It's going to look a little scary, but essentially all that you have to think about is each little dot here, each little circle is actually doing some math. So when you pass an image into a deep neural network or an AI model, it does a bunch of computations in it, almost of the order of billions of computations. And what comes out is something useful. But the problem is that it's hard to identify who's to be blamed when there's 10 billion complications happening? One way to think about it would be that there's an organization, and the organization can achieve amazing things. It has 10 billion employees, they all work together, they do little things, and they can achieve so much together. But once something fails, the problem is you can't identify which one is the cause. Because every employee is doing such little detailed actions that it's a chain of them failing together. And you can't ascertain blame at that point. So the problem with these systems is that there's too much going on inside them, and you can't find which one to blame. So how do you solve this problem? This is a problem people have been working on for many years, and we don't have a clear solution yet. But what I will present today is like a first approach that we've been working on, trying to understand what's going on with these systems. So before I talk about how we started down on this road, I guess I'll just quickly give a story from my past. So my first attempt at understanding this problem was about 4 years ago. At the time I was a research scientist, research assistant at MIT, and I was working with the computer graphics group there. So what we came across was this amazing system by researchers at GHU, Johns Hopkins University, where it would take in this picture and it would say exactly where a car is. So it marks all the regions where the car is. And I started playing with the system, and I played with it pretty much all night. I pumped in about 1,000 pictures. I searched on Google. I searched pictures on Google, and I passed them through the system to see what happens. So I searched what happens if the car has decals. It seems to work. I searched what happens if the car is covered in snow. It still works. But then I found this error. I found that if you have a car that's covered in tarpaulin or in a car cover, it no longer works. I tested this again by finding an example where it was partially covered, and this worked this time. So the understanding from these examples is that if there is a car cover, this AI will not work. Now, there are some good things about this. It seems that we found some failure. Now that we found a failure, we can maybe correct it. But there are some other issues as well. For example, we don't know if it's just the car cover or because something in the background of that picture. Now, I can find more pictures and I can test it, but I can never be sure. Similarly, I may be able to find this picture of a chair and check where the chair is, and it seems to work fine. And then I thought, what happens if you have this chair upside down? So all of us can tell that that's a chair upside down, but this machine cannot. In fact, one of the legs of it appears to be a bottle to this machine. Now, if you look just at that leg, it kind of makes sense why it thinks it's a bottle, but that's not something you want to trust your life with, right? If you're in a self-driving car, you don't want to sit in a system that works like this. So, what do we do about this? First of all, let's try to understand why it is so hard what we did right now. Well, first of all, can we surely be saying that this is because of the viewpoint or because it's upside down? Because maybe the system failed because there's a fence in the back. Maybe it failed because the sunlight is at an angle that doesn't work for it. Maybe it can't handle shadows. You can't be sure, right? So we need to be able to test these things one by one to ascertain blame and say what caused it. This is what we call confounding variables. So there shouldn't be anything confounding, which is something happening simultaneously, and you want to make sure you identify the exact cause for a problem. Starting from this sort of journey of playing around with these systems, sort of gave us an idea as to how we can understand these systems. So at the time I was working in the computer graphics group, and as the amazing volume movie we saw, so one thing that computer graphics allows us to do is to create custom worlds. We can create whatever we want inside the computer. So we created these kinds of pictures. These are pictures of a car in an artificial city that we created. And what we can do here is we can control every little detail of the city. So in the first row, we're showing every detail fixed, but just the viewpoint, that is where the camera sees the car from. In the second row, what we have is motion blur, which is something you would have if we take a picture of a fast moving object. And in the third row, everything else is fixed other than the material of the road. Now that we have all other details fixed and we vary only one thing at a time, we can identify which one of them is to be made. And now we can understand which of these is a problem for machines and then solve it. So building on this idea over the past few years, we worked on a bunch of things. Firstly, here's a motivating example of a project that we worked on. If I showed you just the first picture and I told you that's a Ford Thunderbird, and I'm seeing it from the front, and I showed you the second picture and I said this is a Mitsubishi Lancer and you're seeing it from the side, we as humans can combine these two tasks and say that means that the third picture is the fourth Thunderbird seen from the side. The question is, can machines do this? Humans can, but can machines? And what we found from our work is that yes, if you do it right, machines can do it. If you feed them the right data, if you use the right kind of models, machines can indeed learn multiple tasks simultaneously. And by working on this direction, what we were able to identify is of those 10 billion computations, what kind of computations causes this flaw, and how can we correct it? How do we build models that don't suffer from this problem? Moving on, we try to understand how machines and humans are impacted by what we call object context. So for example, here you have a mug that's placed on a table. That's pretty normal, that's where you find mugs. But what if this mug was flying? As you can see in this picture here, we've removed gravity, so the mug is not flying. In this case, we show co-occurrence, that is, a mug is present in a bathroom or in a garden, somewhere it does not belong usually. And the question is, how are humans and machines impacted by it? And what we find is that there are some interesting findings here. Turns out, humans are extremely susceptible to changes in gravity. If if an object starts flying today up in the air without gravity, human vision is extremely impaired. In fact, machine vision is also extremely impaired, but there are ways to address both of these. Similarly, we find that if you mess up the size, humans are fine, but machines tend to struggle a lot. So that's something that we find where humans and machines don't agree. Now that we've found this flaw, we work on techniques to understand how to fix it. Similarly, we try to understand how machines behave when objects are present in different viewpoints, as we see from different camera positions, and in different kinds of lighting. So each of this is an airplane, which is seen from different viewpoints. And as you can see, this picture is quite different from this picture, right? Humans seem to be handling this perfectly fine. Machines seem to be struggling a lot. Similarly, if you take these toy objects, you place them under the camera and different lights, that's what happens again. But what we do is that by playing with these kind of systems, we're able to understand exactly what causes the flaw, which of those 10 billion computations is to be made, and how do you correct them. So, just talking a little zoomed out, how do we design these experiments, right? This is part of a greater discussion, so I'll just talk about it very briefly. But when we design such experiments, there are some details that are extremely important. First of all, we have something called scientific control. That sounds fancy, but all that I'm talking about here is what we talked about earlier with the chair. How do we know that it's not the upside down chair or the background fence? How do we know which one is to be blamed? The only way to find out is to remove the fence and check the chair upside down. If the system still fails, it wasn't the fence, but the upside down chair that caused the failure. Same goes for the car covers. You remove the background and you check if it's the car covers or the background that's causing the problem. Another thing we talk about a lot is role of random chance. That is, you made a model and it has some failures. Now, how do you know that it's not just this AI that's failing? What if it's just this one model? Then you can just make a new AI and that works fine. So you need to repeat experiments a bunch of times, and that's what we call replicates. So if you ever go into a lab and talk to them about what they do, they tend to repeat all the experiments 3 or 4 times, and then take an average over them to see what happens. But the most important question is, how did I even know that I should be testing upside down chairs or car covers? This is just something that came to mind and I played with it. But there's so many other different things that could be causing failures, right? So how do we know what to test? How do we come up with a complete list of possibilities where things could fail? And the answer to that is, honestly, we don't have an answer. There is no solution to it right now. But I'm going to talk about some things that me and my colleagues are going to be working on over the next few years to understand how to address this problem. First things first, it would be super amazing if you could pass everything into a computer, and computer would automatically test what happens if you change the viewpoint, if you cover the cars with tarpaulin, and all different variations that you can do, and just finds things automatically. That seems like magic, and yes, that is extremely difficult to do. So, what else can we do? If you can't have a system finding and fixing its flaws itself, and if it's just a team of 5 or 6 scientists struggling to cover all the bases, what do we do? How do we solve this problem? The current version of what we think we can do is to include everybody in this room into the experiment. The question is, how can all of us contribute to understanding, finding flaws, and fixing the flaws in the AI? And well, the first one here is a little technically detailed, so I'm going to step away from this one, but I would like to talk a little bit about how we do the second one. The answer to that is building web-based tools and app-based tools that people can play with. So imagine I give you these three pictures that we saw earlier, right? And ask you which one to Most of us will be able to tell us that this one seems to be filled. And then we can also say what's different here is that these cars are covered with paint covers. So it doesn't need to be someone who's worked on these systems for 5 or 6 years to find these flaws. All of us are equipped to find these flaws. All we have to do is make these tools available to each of us to play with them so that all of us can find and fix flaws in the app. On that note, I'd like to end today's presentation, and I'm happy to take any questions on that.